All right, in the last lecture I mentioned we were going to start on Mohr circle, but actually we have something else we need to do first. We need to talk about something called the maximum normal stress state and the maximum shearing stress state. So last time we derived these what are called plane stress transformation equations, which allows us to find our stresses sigma x prime and sigma y prime and tau x prime y prime when we start off with our original stress state. And I'll just sketch it in. Sigma x, sigma y, and tau xy. And we can do this off at any angle that we want. And we can label these new components off in the x prime, y prime coordinate system as sigma x prime, sigma y prime, and tau x prime, y prime. I'm drawing these in their positive directions. We can also show this on the wedge, but with the wedge we lose a little bit of information. We can only have the sigma n, which is the same thing as our sigma x prime, and our tau nt, which is the same thing as our tau x prime y prime. Now the equations that I've written down there on the left are in terms of the double angle, the 2 theta. And it's going to be a little bit more convenient for us to work with those today. So let's talk about these maximum stress states. So if a material is going to fail, it's going to fail because of the maximum stresses in the material, typically. So we can look at 2 conditions, maximum sigmas and maximum shearing stresses. And each of these conditions have their entire own stress state that goes along with it. All right, the values of the maximum normal stress, sigma, and shearing stress tau are important to determine if materials will fail. So let's first take a look at our maximum normal stresses and that stress state. And that has a special name associated with it. Those are known as principal stresses. So the maximum and turns out the minimum normal stresses will act in a set, and that's called the principal stresses. And most books use the symbols sigma p1 and sigma p2, although sometimes some books will change it up a little bit and drop the subscript p, just call those sigma 1 and sigma 2. The book that I typically use is kind of switches at the end. They start off calling them sigma p1 and sigma p2, and then they end up calling them sigma 1 and sigma 2. So just be aware of those different notations. So these are the maximum normal stresses, and again we're talking about what's called a state of plane stress. That means we do not have any stresses that point in the z direction. So sigma z, tau xz, and tau yz are all 0. Now the angle to this special stress state is called the principal angle theta p. So again, imagine that we're taking this stress state right here and we're rotating it to some special angle where, as we do this rotation, the sigmas become maximum. So there's some x prime, y prime coordinate system that we can find where instead of sigma x prime and sigma y prime, we have sigma p1 and sigma p2. Now, I can't tell you right now, until I know the numbers, which ones sigma x prime and sigma y prime are. Sigma x prime could be sigma p1, the maximum, or it could be the minimum, sigma p2. So they turn into the set sigma p1 and sigma p2. We also want to know what happens to tau x prime y prime when we get to these maximum principal stresses. So let's write that down. When we go through that special angle, principal angle theta p. All right, so we're going to have a little bit of algebra today, and we're going to get some equations again, and I'm going to say do not memorize these equations because we're going to use more circle. All right. So let's make a little bit of room. Basically what we're going to do is we're going to take our equation for sigma n, which is the same as our sigma x prime equation, and we're going to maximize that by taking the derivative of that with respect to theta. We're going to solve for the angle theta, and then we're going to plug it back into the equations to see what our stresses are at for that particular value of theta. All right, so let's make a new page. All right, so there's my equation for sigma n. And I'm going to rewrite this just one more time. And I'm going to make a little shortcut here. The sigma x plus sigma y over 2, I'm going to call that sigma average. So I'm going to rewrite this as sigma n is equal to sigma average plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta. So what we're trying to do is we're trying to find the angle theta which maximizes sigma n. So from calculus you know that you can find the maximum value if you take a derivative of the function with respect to that variable and set it equal to 0. So let's take a derivative of this sigma n equation now. The first term does not have any function of theta in it, so its derivative is 0, so that goes away. The second term is a cosine 2 theta. The derivative of a cosine is a negative sign, and because it has a 2 theta in here, I'm going to have minus 2 sigma x minus sigma y over 2 sine 2 theta. And then here we have tau xy sine 2 theta. Derivative of sine is a cosine, so I'm going to have a plus 2 tau xy cosine 2 theta. And then to maximize this, then I will set this equation equal to 0. And when I do that, I'm solving for the principal angle. So I'm going to go back and I'm going to put a subscript on here to make sure that we know that we're talking about the principal angle theta p. Now, to help us solve for the angle theta, let's rearrange this equation just a little bit. We're going to solve for the tangent of theta. We're going to be able to combine the sine and the cosine trig functions. Now the 2's will cancel out here and here. And let's see, if I move this to the other side and then divide through by terms, cross multiply, I'm going to have the sine of 2 theta p divided by the cosine of 2 theta p, which we know is the tangent of 2 theta p. That's going to be equal to tau xy will be on the top divided by this coefficient here, sigma x minus sigma y over 2. Now if we had numbers for sigma x, sigma y, and tau xy, we could punch that directly into our calculator, take the inverse tangent, and then divide it by 2, and we can find the value of theta. And then we take that value of theta, theta p, and plug that back in to this equation, and we can find the maximum stress based on this sigma x prime equation. What we want to do for now, though, is we want to leave this in equation form because we want to explore these equations a little bit. Sometimes when you work with equations, you learn more by leaving them in terms of symbols than you do if you put in numbers for everything. So let's talk about this, what we have right here. We have the tangent of 2 theta p. We know that we're going to get a couple of roots in 360 degrees because we're dealing with trig functions, and it's got a 2 theta. And we'll talk about those roots a little bit. But we're going to do something maybe that you may have seen in some class, you may not have, but we're going to interpret this tangent graphically. I'm going to leave a little space to the left, and I'm going to draw in a triangle. And we know that one interpretation of the tangent is the opposite over the adjacent side. So in this triangle, if I call this angle here 2 theta p, then the opposite side can be tau xy, and this side over here is going to be sigma x minus sigma y divided by 2. And you can see that that works out. The tangent of 2 theta p would be tau xy over sigma x minus sigma y over 2. If I go up to this equation, I want to maximize it in terms of symbols. What I need in terms of symbols is the cosine and the sine of 2 theta p. I can get that from this triangle that I just drew. We need to figure out the hypotenuse of the triangle, and for reasons that will be apparent later, I'm going to call this hypotenuse r. We can find the value of the hypotenuse by the Pythagorean theorem. R squared is going to be equal to tau xy squared plus sigma x minus sigma y over 2, quantity squared. And we can find values for the sine of 2 theta p, which in this case would be tau xy over r, and the cosine of 2 theta p, which would be sigma x minus sigma y over 2 over r. Now I did mention that we actually have two roots in 360 degrees. We have the one root theta p. I'm going to label that as theta p1. And we have another root that's 180 degrees away from 2 theta p1. I'll call that 2 theta p2. I'm going to dash that in on this left side. It's going to be like a reversed and mirrored image, so it's flipped over. So the angle 2 theta p2 will be this large angle, but it's kind of like this angle is the same, except it's in this quadrant over here. And in this quadrant, we have a downward magnitude of tau xy, and we also have a magnitude this way, which is the same, sigma x minus sigma y over 2. And we have the same hypotenuse, r. So I can find the sine and cosine of 2 theta p2, and that's pretty easy. We just have to throw in a negative sign in here, and so we have minus tau xy over r, and a minus sigma x minus sigma y over 2 over r. So those are the two roots that will satisfy that equation. So what we can do then is to find the values of our maximum and minimum normal stresses is to plug them into the sigma x prime and sigma y prime equations. All right, so let's save this page and we'll get set up to show that. All right, so let's take a look then. We're going to plug in these values of sine and cosine 2 theta p into the sigma n or sigma x prime equation. So let's do theta equal to theta p1. And so we get what's going to be sigma p1, our first principal stress from this equation. It's going to be sigma x plus sigma y over 2. We said we would call that sigma average plus this quantity sigma x minus sigma y over 2. Cosine 2 theta p1 is the quantity sigma x minus sigma y over 2 divided by r, and then we're going to have plus tau xy times the sine of 2 theta p1, which is tau xy divided by r. Now if we look at these last two terms, they have a common denominator. So what we're going to do is we're going to pull that out front. And we're going to be left with sigma x minus sigma y over 2 squared plus the quantity tau xy squared. Now, if you recall from the previous page, on the previous page, we denoted that as r squared. That was the hypotenuse of our triangle. So this reduces down to sigma average plus r squared over r. Of course, one of those r's cancel out. And what we have is sigma p1 is equal to sigma average plus this quantity r, the hypotenuse of the triangle that I just showed. For our second root, our minimum, sigma p2 would be equal to sigma average. And then the only thing that's different would be the negative sign in those expressions. So we have sigma average minus that quantity r. Let's go ahead and write down r, where r is equal to the square root of sigma x minus sigma y over 2, quantity squared, plus tau xy, quantity squared. And again, this is for theta p equal to the inverse tangent of tau xy over sigma x minus sigma y over 2, and then the quantity all over 2. All right, so those are the stresses, the normal stresses, the sigmas. But let's see what happens when we put in the value for theta p1 into the equation for tau x prime y prime. All right. Okay, so again, this is for theta equal to theta p1. The tau x prime y prime equation will be equal to minus sigma x minus sigma y over 2 sine 2 theta p1, which is tau xy over r. Then we're going to have plus tau xy times the cosine of 2 theta p1, which is sigma x minus sigma y over 2 divided by r. Well, look what happens here. Those two terms are the exact same magnitudes but opposite sign, so those will cancel each other out, and we're left with 0. This is something that's really important. I can't emphasize this enough at this point. When you have maximized your normal stresses, your shearing stresses will vanish. Your shearing stresses will be 0. So let's put that in a bright color and write that down. The maximum and the minimum sigmas go together. So when you have maximum and minimum normal stresses, the shearing stress at this orientation is 0. Again, that's kind of important. All right, so we maximized our sigma x prime or our sigma n equation to find the biggest principal stresses. And you can imagine there is something called a failure criterion called the maximum principal stress theory of failure, where if your biggest principal stress exceeds the strength of the material will break. So it's a very practical application of maximizing this stress components. And another thing I want to point out is it doesn't matter what orientation you start out in for your stress state. If you have any combination for any angle theta, this will be the maximum for every angle of theta that we have. Right. So the next thing we're going to do is something very similar. We're going to maximize the tau x prime y prime equation. So let me get set up for that. All right, so let's look at our maximum in-plane shearing stress state. We're going to start with our equation tau x prime y prime, or tau nt, is equal to minus sigma x minus sigma y over 2 sine 2 theta plus tau xy cosine 2 theta. And we go through and do the same kind of steps that we did for sigma x prime to maximize it. What we're going to do then is, let's label this as tau nt. We're going to take the derivative of this tau nt with respect to theta and set it equal to 0. So we don't have that sigma average term on this one. We have sine of 2 theta. The sine, derivative of sine is a cosine, so we're going to have minus 2 sigma x minus sigma y over 2 cosine 2 theta. And then derivative of cosine is minus sine, so we'll have minus 2 tau xy sine 2 theta equal to 0 to maximize it. And when I maximize it, I'm going to label the subscript s on my theta, so that denotes the theta s is the angle to the maximum shearing stress state from my x-axis. All right, so we can do something similar to what we did before, where we can separate these up and we can write this as a tangent. Sine over cosine is a tangent, so we can have the tangent of 2 theta s is equal to, well, these 2's will cancel out. We'll have a minus. Now up on top, this time is sigma x minus sigma y over 2, and on the bottom is the quantity tau xy. Now this is kind of interesting. It looks very similar to what we had for the tangent of 2 theta p. Let's just write down in parentheses what we had for the tangent of 2 theta p to get to the maximum shearing stress state. We had positive tau xy over the quantity sigma x minus sigma y over 2. So if you compare these two and contrast them, the difference is that one is the negative reciprocal of the other. So if we can interpret the tangent of a line as its slope, we know that the slope of two lines that are negative reciprocals of one another are going to be perpendicular. So this makes a lot of the math easy for us. Now we can say that the angle 2 theta s is equal to the angle 2 theta p, let's label it as 1, plus, well, or we can go minus 90 degrees. If we divide through by 2, we can say that the angle theta s for maximum shear is the principal angle theta p1 plus or minus 45 degrees. Remember at the very beginning of the course, we had a bar in tension, and we said that the maximum shearing stress was at a 45-degree angle to the axis of the bar. Well, the axis of the bar was the principal angle. That was the direction in which the stresses were maximum. And so we can go plus or minus 45 degrees from that principal stress axis to get to our maximum shearing stress. It's perfectly consistent to what we have. We also had a case when we looked at torsion of a bar. Pure torsion gave us a maximum shearing stress state at 0 degrees and maximum sigmas at plus or minus 45. In that case as well, the shearing stress state is 45 degrees from the maximum normal stress state. Theta s goes with the shearing stress, theta p goes with the normal stress state. I know I said that kind of fast. I'll draw some pictures here in a moment. Well, if we want, we can go and we can construct that triangle like we did before, and we can put in values for 2 theta s1. There's going to be another root. We can put in the values for 2 theta s2. I'm not going to go ahead and take the time right now to construct that triangle. I'll let you do that if you'd like. But we can take those values for 2 theta s1 and 2 theta s2, and plug them back into the tau x prime y prime equation. And what we will get after we do the algebra is that will reduce down to be the hypotenuse of that triangle R. So the maximum, what's known as the in-plane shearing stress, will be the hypotenuse of that triangle that I constructed a few pages ago, the quantity R. Now I'm going to call this an in-plane maximum. We will talk about out-of-plane maximums in a little while, but this is an in-plane maximum because it's in the XY plane. Just like we did with normal stresses to find the maximum principal stress, we also were interested in finding out what the shearing stress was for the theta P1 angle. That turned out to be 0. We also want to find out what the maximum normal stress is, what the normal stress is when we have maximum shearing stress. Be careful how I say that. We want to find out what the normal stress is on the planes of maximum shearing stress. So we would go back to our sigma n equation and plug in 2 theta S1, the sine and the cosine of 2 theta S1. And what we would get when we do that is theta equal to theta S1. The terms with the sines and the cosines cancel themselves out, but we're still left with the term that has sigma average. Okay, so the trig function terms cancel themselves out, but we still have this term sigma average that did not have the sines and cosines in it. All right, so this is also very important. On planes of maximum shearing stress, we have average normal stress. So let's write that down in red like we did for the other one. Okay, so one more time, on planes of maximum shearing stress, we have a normal stress, a sigma average. Well, let's draw a picture to kind of illustrate all of these concepts. So what we did is we started off with our original stress state. Let me go to the blue color. This is a little square I'm trying to draw. And on this stress state, we had these stresses, sigma x, sigma y, and tau xy. Now, I'm drawing them as if they're positive, but they could have any values, positive or negative. And then we were able to, based on those numbers, find the value for theta p, because the tangent of 2 theta p is tau xy divided by sigma x minus sigma y over 2. If we have those numbers, we take the inverse tangent of the right-hand side divided by 2 to get theta p. Now, theta p could be positive or negative, but just to draw this, let's suppose it's counterclockwise. So now we're in the principal stress state. The principal stress state has maximum sigmas. I don't know which one is which right now. This could be sigma P1 and this one could be sigma P2 or vice versa. but it will have it either that way or the opposite way. But the point is, it has no shearing stress. The value of the principal stresses, you write it this way, sigma P1 and sigma P2 is equal to the average normal stress plus and minus this R term, where the quantity sigma average is sigma x plus sigma y over 2, and we said R was the square root of sigma x minus sigma y over 2, quantity squared, plus tau xy squared. Now, I don't want you to memorize these equations. I do want you to understand how to use them, but again, when we do more circle, all of this stuff will make be a lot easier to remember. Let's just put it that way. Okay, so this is the maximum principal stress state. There is no shear. Its value is 0 in that orientation. And we know that plus or minus 45 degrees from that stress state is the maximum shearing stress state. So let me draw it this way. I can go either way. From that axis to here being 45 degrees, my maximum shearing stress state will have shearing stresses on it, and these arrows could point in this direction or they could all point in the opposite direction. I can't tell right now unless I have the numbers, but the value of that maximum shearing stress in plane, in the xy plane, will have the value of R, that hypotenuse of that triangle that I constructed, and in addition to that, I have normal stresses all the way around that are equal to the value of sigma average. Now, I drew these off to the right of my original block, but really all of these things are happening right on top of that point right here. So these stress states, you can imagine just taking the square and rotating it to these orientations. Okay, so this stress state down here would be known as our maximum shearing stress state. All right, so I did write down some equations here. Again, I don't want you to memorize those. The one last point I want to say again, maybe I should write this down, is without knowing the values, of sigma x, sigma y, and tau xy, I can't say if the stress state is this being sigma P1 and this being sigma P2, or if the stress state is this being sigma P2 and this being sigma P1, where sigma P1 is the average plus R, sigma P2 is the average minus R. I can't say that without knowing those numbers. This is a disadvantage of using these equations blindly. Everything will be much more clear in that regard when we do learn about more circle of stress. All right, so that's what we want to talk about with these maximum values. Usually there's some homework problems where you sketch the stress states off at some angle like I have shown here, and find the values of the maximum normal stresses, sigma P1, sigma P2, and the value of the maximum in-plane shearing stress, which would be equal to this equation for R. All right, so we'll get ready for more circle now, and we'll do that next.